All right, so some definitions we've already done, so we'll do them quickly. But thermal was this science relating energy, heat, work, and temperature. What was the definition of energy? The capacity to do work. There's a second line after it. What was that? It was the ability to have what? Produce effect or produce a change, that you can just cause a change of some kind, right? The capacity to do work is your book definition. Oh, what's the definition of work? How about this? If I say that work and heat are both energy transfer, what's the difference between heat and work? Yes. Perfect. Organized versus random motion. And what that typically means for us is we're either talking about a macroscopic amount of like measurable, detectable movement often. Work is force times distance, something moved over a distance for us in terms of work, versus heat is at this microscopic level, this change in kinetic energy going on due to a temperature difference. But heat and temperature were not the same, right? So we have energy transfer by this organized motion, a method of moving energy from one system to another. Heat was our random motion. Okay, so energy transfer that will typically result from a temperature difference. And like I said, I like to think of this more at the micro scale versus a macro scale. What was the definition of, so dynamics was sort of the misnomer. Why was that kind of a poor or a weird name for studying this stuff? Because what are we usually interested in? Statics. The word that we're going to use is equilibrium, okay? So sort of when we think of the opposite of dynamics, we think of statics. Equilibrium is really generally what we're more interested in thermo. Reaching equilibrium, what do we do to reach equilibrium? Once we get there, what are all our values at? Let's calculate all of them. So equilibrium defines the state of a closed system when there are no net changes to macroscopic properties. So if I plot these macroscopic properties versus time, volume versus time, pressure versus time, temperature versus time, what do those plots look like for equilibrium? Yeah. Straight horizontal lines. Okay? So on a macroscopic scale, I have constant properties. We haven't introduced entropy yet. S is our entropy, but all of this stuff is not changing with time. Global properties are stable. And then, of course, we know at a microscopic level, things are moving and colliding and exchanging energy. There's just no net change. What is the definition of a system? What's the other thing besides a system? What's our other option? I think I heard someone say the entire universe. The system is the region that contains everything we are interested in. And most of the time I will tell you what system we're interested in. Okay? But the reason we have to do this is because to make the thermodynamics manageable, we have to restrict our focus. If we don't isolate, this is the area we're actually talking about the heat going in and out, we can't do any of the math, okay? The boundary is, not surprisingly, what separates the system from the surroundings. And so this is the environment, whatever's interacting with it. And then those are kind of the only two options in every given scenario. You're either the system or you're the surroundings, and those things add up to the universe, okay? And for our purposes, we generally, if I'm a system and Justin's a system, we don't interact with each other in all our storylines. And we're in the universe, but he's just my surroundings, like, who knows? We're gonna keep it pretty simple in this class, okay? So what do you think a closed system is? Or what's an open system? Yeah.
A closed system doesn't interact with the surrounding, and the open system is the opposite.
Okay, so he said the closed system isn't interacting with the surroundings, and the open system is, and it's pretty close. Okay. So here we have a couple different versions. An open system, both matter and energy, so mass, actual stuff, can interact and exchange with the surroundings, and energy, either in the form of heat or some actual work that we're doing. Closed means matter or mass isn't being transferred, but heat or work potentially could still be done. Okay, different types of energy transfer could still happen. And isolated means nothing gets in or out, okay? Isolated is a really nice one. I don't know if I ever did it last time, but what we'll find as we move forward next week, if it says isolated, a whole lot of stuff just gets to go to 0, and you don't really have to do anything. Okay? So here are the definitions again. Open, I can exchange energy and mass. Closed, I can exchange types of energy, but not mass. Isolated, neither. Okay. Here's a super sophisticated example, okay? So in our open coffee cup, this is open because, you know, if I let the coffee be the system, I guess I could call I maybe could call the cup the boundary and let the outside be the surroundings, or I could actually consider the fact that whatever the ceramic is my surroundings. Lucky for you, you don't take thermo, unless you choose to. You're not taking thermo and MSE here, where you would do a problem that's like coffee's in a cup at this temperature, and it's made out of this type of polystyrene, and you wait this long, and now how cold is your coffee? Like, that's a literal problem I did. Or the gold bar sits on the nickel table in a nitrogen environment, what happens? It's not exciting. I actually think some of the biological applications get way more exciting. Okay? In our closed system here, so here we have evaporation, maybe we spill the coffee if you're me. Here we have a lid on it, so it's closed, the mass can't get out, but I know that if I touch this, heat could still flow into my hand if it's colder than the coffee. And then we have a thermos, okay? We're gonna call the thermos the isolated system. And the word that you will know that I'm talking about isolated in terms of heat flow is the phrase perfectly insulated. If you see the word perfectly insulated, I'm claiming that heat can't flow in and out, okay? Doesn't really happen in real life ever, but let's pretend it could. Perfectly insulated would be our isolated system.